In this video, we'll be looking at the QuickSort algorithm. QuickSort uses recursion to implement a divide and conquer strategy to sort an array. The first step is to choose a pivot element, which is usually the last element, so let's make it 5. We then compare every element in the array to the pivot, and we'll place it in one of two groups. It's either less than or equal to the pivot, or greater than the pivot. So let's start by looking at the first element, 8, which is greater than 5. When the element is greater than the pivot, we actually don't need to do anything. By just leaving it there, we automatically add it to the greater than section. Next we'll look at 1, which is less than 5. Well, in QuickSort, elements that are less than the pivot should be on the left side of the array. So the way we do this is to swap the current element with the leftmost element that's in the greater than section. Right now, we only have one element so far that's greater than the pivot, so we'll just swap these two and we can move on. Next up is 6, which is greater than 5. Again, we don't need to do anything, and it automatically gets added to the greater than section. Next is 4, which is less than 5. The leftmost element in the greater than section is now 8, so we swap 8 and 4. Next is 0, which is less than 5. The leftmost element greater than the pivot is 6, so let's swap 0 and 6. Next is 3, which is again less than 5, so we'll swap it, this time with 8. Lastly, we look at 9, which is greater than 5, so we can just leave it there. Now at the end, we have to make one last swap to bring the pivot to the correct place. We do this by swapping the leftmost element that's greater than the pivot with the pivot itself. Now everything to the left of the pivot is less than or equal to the pivot, and everything to the right is greater than the pivot. Because of this, we know that the pivot, 5, is now in its final correct position. All we need to do now is recursively sort the two subarrays. Let's run QuickSort on the left side first. The pivot will be 3. 1 is less than 3, so normally we would swap, but since we don't have any elements yet that are greater than the pivot, we can't really swap it with anything, so we just move on. Next is 4, which is greater than 3, so we just leave it there. Next is 0, which is less than 3. Now we do need to swap. There's only one element that is greater than 3, so we can just swap these two to put them in the correct positions. Now we're done with the comparisons, and we'll just do the final swap with 4 and the pivot. The pivot, 3, is now in the correct spot, and we call QuickSort again on the left subarray. 0 is the pivot, and there's only a single comparison to make. 1 is greater than 0, so we just leave it. We do the final swap, and now 0 is in the correct place. At this point, we're done with all the left subarrays, so now we need to call QuickSort on the right subarrays. But notice that there's only one element in this right subarray. This means that we've reached the base case. If we know that 0 and 3 are in the right spots, and there's only one element between them, then that must mean that that element is in the correct spot as well. So 1 is sorted. And the same logic applies for 4. We know that 3 and 5 are in the correct spots, so 4 must be sorted as well. Now we'll move on to the right subarray that isn't sorted yet. The pivot is 6, and the first comparison will be with 8. 8 is greater than 6, so we leave it there. 9 is also greater than 6, so nothing changes. All we do is the final swap with 8, and now 6 is sorted. Now we call QuickSort one more time to sort the rest. 8 is the pivot, and 9 is greater than 8, so we just leave it there. We do the final swap, and now 8 is sorted. 9 is the only element left, and since we know that everything else is sorted, that must mean that 9 is also sorted. Now the entire array is sorted, and we are done. Now let's look at the code and see how this idea is implemented in practice. So to the right are the two functions that make up QuickSort. Most of the work is actually done in the partition function, and the QuickSort function at the bottom really just manages the recursion. Both functions take in the array to be sorted, and two parameters called low and high, which will set the bounds for whichever part of the array we need to work on. Since QuickSort uses recursion, I'll also use this diagram of the call stack here, so we can keep track of which function we're on. So to start, let's call QuickSort and pass in this array on the left. We have to sort the entire array, so we'll pass in the starting and ending indices, 0 and 7. The first test is to see if low is less than high. In other words, there must be at least two elements in the section of the array that we're working with. Otherwise, we've hit the base case and there's no need to sort it. 0 is less than 7, so we continue. Next is to call the partition function with the same low and high bounds, so 0 and 7. I'll also push it to the top of the call stack here, since we're entering a new function. Next, we'll set the element at the high index as the pivot, so here it'll be 5. Then we'll create a variable called I that's initialized to low minus 1, so here it'll be -1. This variable will separate the elements that are less than the pivot from elements that are greater than the pivot. Next, we enter a for loop that'll go from the low index to 1 before the high index, and determine if each element in that range is either less than or greater than the pivot. Low equals 0 here, so j will start at index 0, which has a value of 8. Now we compare the two. 8 is greater than 5, so we skip this if block and just go on to the next iteration. Now 1 is less than 5, so now we enter the if block and do the swapping. First we'll increment I by 1, then swap the ith element and the jth element. Next we look at 6. 6 is greater than 5, so we continue to the next iteration. 4 is less than 5, so we'll swap again. We increment I, then swap the ith and jth elements. Next is 0, which is less than 5. We'll increment I again, then swap 0 and 6. Now let's pause here for a second. You can see that QuickSort always maintains 4 regions of the array. First is all the elements that are less than or equal to the pivot, which is everything from index I and to the left of it. The second region is elements that are greater than the pivot, which is everything between index I and j, including j. The third region is unknown elements because we haven't gotten to them yet, which is everything between the j index and the last element. And the final region is the pivot itself, which is just the last element in the array. Now let's finish this up. Next is 3, which is less than 5. We do the same thing by incrementing I and swapping 3 and 8. The last comparison is with 9, which is greater than 5, so we just leave it. Now we exit the loop and perform one last swap between the I plus 1th element and the pivot. I equals 3, so let's swap the element at index 4 with the pivot. Now the pivot's in the right place, and everything to the left is less than or equal to the pivot, and everything to the right is greater than the pivot. And as we mentioned earlier, this means that the pivot element, 5, is in its final spot and doesn't have to be moved anymore. The function then returns the index of the pivot, which is I plus 1, or 4 in this case. Let's exit the partition function and return back to the QuickSort function. The value of piv is 4, so I'll make a note here in the call stack that piv equals 4, so we don't forget later. Now we recursively call QuickSort twice to sort the remaining portions of the array. Let's start with the left side. We'll call QuickSort and pass in 0 as low and piv minus 1 as high. Notice that we're omitting piv, since the element at the piv index is already sorted. I'm also going to put a green dot here that matches the color of the function in the call stack, so we know exactly where we left off. Piv equals 4, so this new QuickSort call is going to have 4 minus 1, or 3, as the new high bound. 0 is less than 3, so let's call partition again and pass in 0 and 3. 3 will be the pivot, and I will start at -1 again. Now we start the comparisons. 1 is less than 3, so we'll increment I and swap. But notice that I and j are pointing to the same element, so we're actually swapping 1 with itself, so nothing happens. Next is 4, which is greater than 3, so we just move on. 0 is less than 3, so let's increment I and swap 0 and 4. The loop is finished, and now I plus 1 equals 2, so let's swap the pivot with the element at index 2. Now partition is done, and we return 2 as the pivot index. Now that we're back in the QuickSort function, we have to call QuickSort again recursively. Again, I'll make a note here that piv equals 2, and we'll call QuickSort on the left side of the array. The new QuickSort call will have 0 and 2 minus 1, so 1, as its low and high bounds. Again, I'm leaving a purple dot here, so we know where we left off on the purple function. We're now starting to approach the base cases, so I'm going to go through these a little quicker. 0 is less than 1, so let's call partition with 0 and 1 as the low and high bounds. The pivot will be 0, and there's only one comparison to make. 1 is greater than 0, so we just skip to the final swap. I plus 1 equals 0, so we'll swap the 0th element and the first element and return 0. Piv equals 0, so that means the next recursive call will pass in 0 and -1 as the low and high bounds. Now 0 is greater than -1, which means we've hit the base case. There's nothing here to sort, so we just exit. We're now back in the quicksort call, where low equals 0 and high equals 1. We can see with the blue dot where we left off, so now let's move on to the second quicksort call, which will now pass in piv plus 1 as the low bound. Piv plus 1 equals 1, and high also equals 1, so this quicksort call will pass in 1 and 1. Again, 1 is not less than 1, so we just exit. Notice that since we passed in a section of the array with only a single element, which was the element at index 1, that means that the element is already sorted and in the correct place. We're now entirely done with this quicksort call in the blue, so let's pop that off the call stack and return to the quicksort call with 0 as low, 3 as high, and 2 as piv. We can see where we left off with the purple dot, so let's move on to the next quicksort call. Piv equals 2, so piv plus 1 equals 3. So we'll pass in 3 as low, and high also happens to be 3 as well. It's the same case as the last time. Let's exit, and now we're done with the function in purple. We're now back to the green function where the bounds are 0 and 7, and we have to do the second quicksort call on the right half of the array. Piv equals 4, so we'll pass in 5 as low and 7 as high. 5 is less than 7, so let's call partition. 6 will be the pivot, low is 5, which means that I will start at index 4 and j will start at index 5. 8 is greater than 6, so we move on. 9 is also greater than 6, so we're done comparing and we just swap 8 and 6. I plus 1 equals 5, so piv equals 5. The next quicksort call will then pass in 5 as low and 5 minus 1, or 4, as high. 5 is not less than 4, so we just exit. Now we try the right side of the array and pass in 5 plus 1, or 6, as low, and 7 as high. 6 is less than 7, so let's call partition. 8 will be the pivot, and we just need to compare it with 9. 9 is greater than 8, so again, we just skip to the final swap. I plus 1 is 6, so we'll return that, and now these last two quicksort calls will be our last. Since piv is 6, we'll first pass in 6 and 5 as the bounds. 6 is not less than 5, so we exit. Next we try 7 and 7. 7 is not less than 7, so again we exit. Now we return to the dark blue function, but we just finished executing the last line of code. So we exit that function and go back to the orange function. Well, we just finished that too, so now we're back at the very first function call, the green function, which we also just finished executing. So we exit the last function, and we are finally done. The entire array is sorted. Now let's look at the big O analysis by drawing a recursion tree. In the best case, the pivot element will end up being placed in the middle of the array, or as close to the middle if there's an odd number of elements. In other words, the pivot is the median. That way, with each recursive call, the array is split roughly in half. It's not going to be exactly half. For example, in this case, one is n over 2, and the other is n over 2 minus 1, because we exclude the pivot element. But because we're subtracting a constant, we can just ignore that minus 1 for big O purposes. Now this pattern will keep continuing. With each recursive call, the arrays will be split roughly in half until we reach the base case of only one element. So if we keep dividing by 2 with each recursive call, how many levels of this tree are there? This is a very common pattern in recursion, and it turns out that the height of this tree is O of log n. It's actually a log with base 2, but with big O we can leave out the base, so I just left it out here. Now let's look at how much work is done at each level of the tree. At the top level, the for loop will execute for each element in the array, excluding the pivot, so there's n minus 1 iterations. So that's O of n. At the second level, we also have to iterate for each element in the array, but we also don't need to iterate over the new pivots of each subarray. That's a total of 2 less elements, so that's n minus 3 iterations. The key thing here is, again, even though there's less elements, each time we're subtracting by a constant. Each recursive call reduces the number of elements you need to iterate over by 1, which is a constant and has nothing to do with n. So the intuition here is that, disregarding the subtraction of all the constants, at each level you have to iterate over the entire array, so each level runs in O of n. Now that we know that each level runs in O of n, and there are O of log n levels, to find the total number of steps, all we need to do is multiply the number of steps in each level by the number of levels. So in total, QuickSort runs in O of n times log n in the best case, which is really good. Now let's look at the worst case. The worst case happens when the pivot element is either the largest or the smallest element in the array, since this leads to a completely unbalanced tree. Let's say that the pivot always happens to be the largest element. Then the length of the array of the next recursive call will be n-1, then n-2, and so forth until we finally reach 1. For the first level, we would have to iterate through n-1 elements. The second would be n-2, and so on until we hit 1. Now there are n levels in the tree, not log n levels, so how many steps is that in total? We can use this formula here that tells us that the sum from 1 to n is n times n plus 1 over 2, or n squared plus n over 2. So to find the sum to n minus 1, let's take n squared plus n over 2 and just subtract n from it. After a bit of manipulation, we can see that this ends up being n squared minus n over 2. And since with big O notation, we only take the dominant term and drop constants, this ends up being O of n squared. The proof for the average case is kind of complicated, so I won't go over it here, but it turns out that the average case is still O of n log n. But what if we're in a situation where the worst case keeps happening often? For example, what if we keep receiving arrays that are already sorted or reverse sorted? Then the pivot would always be either the smallest or largest element, and the algorithm would keep running in O of n squared. To solve this, we can use a modified version of QuickSort called Randomized QuickSort. In Randomized QuickSort, we pick a random element of the array and swap it with the last element. We can then continue on with QuickSort normally, except now the pivot will always be random. By doing this, we can ensure that even if the last element is consistently the largest or smallest element, it's very unlikely that we keep on picking the largest or smallest element as the pivot, and so on average, QuickSort will run in O of n log n.